This week we will learn about conservation of momentum. More importantly, we will learn about collisions. This lecture pairs with Lab 5, which starts this week. Content presented in this lecture will be helpful in your data analysis. The learning objectives for this lecture are to identify the different types of collisions, apply the universal accounting equation to conservation of linear momentum in a collision problem, and understand what equations to use when analyzing your data from Lab 5. Let's start with an overview of Lab 5. Today we're astronauts studying moving space junk. Satellites are flying around. Stuff is hitting other stuff. Collisions. Things are flying in many directions. Okay, so maybe it's not quite like what I described, but in Lab 5, you will be analyzing the data of two asteroids, pucks, colliding at different velocities and angles, then determining if momentum is conserved and the elasticity of the collision. When multiple objects collide, we want to be able to track the position and velocity of all objects in 2 dimensions. We also want to calculate the collision angle using the data from the tracking camera. We need to calculate the initial and final momentum of our objects to check if momentum is conserved, and finally, we need to calculate the initial and final kinetic energy of our objects to determine the elasticity of the collision. This lecture will help you figure out how to do all of these things. Task 1. Tracking multiple bodies is a continuation of what you've done for your previous labs, except you won't be the one to collect the data. From the provided data file, you will need to identify the position of the 2 pucks, obtain the components of the velocity vectors, then calculate collision angles. You are free to write your own Python code or do your calculations in Excel. Now for task 2, we need to find the collision angle. We could use the position data of the pucks. Each path can be approximated by a linear equation. Just create a linear trendline in Excel and use the line_st function to find the uncertainty of the slope. Or how about an easier option? Use the velocity vectors. The dot product theorem states that the dot product of 2 vectors is equal to their magnitudes multiplied together with the cosine of the angle between them. For each collision, calculate several estimates for the collision angle using the velocity data for different time frames. Then, calculate the average to use as your collision angle and the standard error, the standard deviation of the means, to use as your uncertainty. Since this lecture is about conservation of momentum, we can infer that momentum is always conserved in a collision. This is true. When objects collide, momentum is neither generated nor consumed. It remains constant throughout the collision, no matter the type. However, kinetic energy of the objects involved in the collision may or may not be conserved. For collisions where kinetic energy is not conserved, it is converted, dissipated, into thermal energy, heat, as well as internal elastic potential energy via deformation. If an object deforms during a collision, then kinetic energy is not conserved. When 2 objects collide, we can classify the collision as one of 2 types, elastic or inelastic. More on what these are in the next few slides. Let's talk about elastic collisions first. In an elastic collision, momentum is conserved and kinetic energy is also conserved. Both remain constant throughout the collision. After the objects collide, they separate and go off in different directions. A toy called Newton's cradle, shown on the right, is a great example of elastic collisions. The metal ball on one end strikes the line of unmoving hanging balls and transfers all of its momentum and kinetic energy through them to the last ball, which swings out, then falls back and repeats the action. A large Newton's cradle can be found on the first floor of Zachary, outside the Fisher Design Center. Next time you pass by, think of all the momentum and kinetic energy being conserved. Next is inelastic collisions. In an inelastic collision, momentum is conserved, but kinetic energy is not conserved. Some of the object's kinetic energy is used up when it deforms as it hits a surface or other object. On the top right, we can see a golf ball deforming as it hits a wall and bounces away. High-speed videos are very useful when taking data of collisions. We can play it back at a slower frame rate and see just how much the object deforms. On the bottom right, we can see a tennis ball deforming as it hits the floor and bounces back up. Tennis balls are known for being bouncy and easily deformed, but many people are surprised to learn a golf ball can be deformed by just as much. Now let's talk about perfectly inelastic collisions. I know, I said there were only 2 types of collisions, but I sort of lied. A third type of collision, a perfectly inelastic collision, happens when 2 or more objects collide and stick together. They move at the same velocity after the collision and can be treated as a single body. The maximum amount of kinetic energy is lost during a perfectly inelastic collision due to bonding the objects together. Let's summarize the 3 types of collisions. In an elastic collision, objects are not deformed and both momentum and kinetic energy are conserved. In an inelastic collision, objects are deformed and lose some kinetic energy. Momentum is still conserved. In a perfectly inelastic collision, objects are joined together to form one body, the maximum amount of kinetic energy is lost, and momentum is still conserved. Plain old inelastic collisions are the most common types of collisions seen in the real world. The kinetic energy lost during these collisions typically converts to friction, sound, and heat. Now for the math part. The conservation of momentum equation can be used for all types of collisions. Momentum is the mass of an object multiplied by its velocity and is typically written as the letter p. Since velocity is a vector, that means momentum is also a vector. We can start with defining our system, then applying the universal accounting equation. In general terms, our system will contain 2 objects, have a time period of just before to just after a single collision, and will count momentum. Since momentum is conserved, the generation and consumption terms are 0. There will be no input or output of momentum during our specified time period, so those terms are also 0. That leaves us with the general equation final amount equals initial amount. We have 2 objects in our system, so we can calculate their momentum separately. The initial momentum of object 1 plus the initial momentum of object 2 equals the final momentum of object 1 plus the final momentum of object 2. We normally use a subscript I for initial and F for final. For a perfectly inelastic collision where the 2 objects stick together, we can simplify the right-hand side of our equation with just one final velocity. The kinetic energy equation will only work for elastic collisions where there is no loss of kinetic energy. It is the same idea as the momentum equation. 1/2 of the sum of the initial kinetic energies of the objects is equal to 1/2 of the sum of the final kinetic energies of the objects. For our fourth and final task for Lab 5, we need to determine the kinetic energy released during a collision. The amount of kinetic energy lost will only be non-zero for most inelastic collisions and will depend on how much the objects deform and how the objects combine to stick together. In Lab 5, the pucks will not stick together. They will collide, then separate, and move in different directions. Therefore, this experiment is an elastic collision with no kinetic energy lost. Or is it? Do the pucks deform? Are you losing kinetic energy in some other way? What equations will you need for Lab 5? For Assignment 1, you will need the general momentum equation for elastic and inelastic collisions to determine if momentum is conserved. Hint, it should be. Your pucks shouldn't stick together after the collision, so you won't need to use the momentum equation for perfectly inelastic collisions. For Assignment 2, you will need the kinetic energy equation to determine if the collision is elastic or inelastic. If both sides come out equal, within some tolerance, i.e. error, your collision is elastic. If both sides come out to different values, no overlapping errors, then your collision is inelastic. What about two dimensions? The pucks are thrown at each other from more than one angle, so the experiment is done in two dimensions, the xy plane. Velocity and momentum are both vectors, so you can split up the momentum equation into x and y components for a total of two equations. In a few slides, we will look at an example to see how this works. But what about problems where we don't know the mass of an object? If we're studying asteroids or space junk, we don't always know the mass. So let's calculate it. In this type of problem, we know all velocities and collision angles, but we don't know the masses. Can we use the momentum equation? Of course! In this collision, there are two objects. Object 1 has a mass of m1 and an initial velocity traveling only in the x direction. Object 2 is initially at rest. After they collide, Object 1 flies off at an angle theta and Object 2 flies off at an angle phi. Let's calculate the mass of Object 2. First, we need an equation. Let's pick the y component of the momentum equation. Object 2 is initially at rest, so we can set that term to 0. Object 1 is initially moving only in the x direction, so that term is also 0. Then we simplify, add some geometry, sign to get the y component of velocity, and rearrange to solve for the mass of Object 2. We could have used the x component of the momentum equation, but the answer would not have been as pretty. Let's look at another example using three bodies. We still know the mass of Object 1, Objects 2 and 3 are initially at rest, and we know all of the angles for the final directions of all the objects. This particular example uses angles greater than 90 degrees and 270 degrees so that all terms in our equations have a plus sign in front of them. You can use acute angles in your solutions. Just remember to add a negative sign if the velocity is in the negative x or y direction. Now we calculate the masses of objects 2 and 3. We have two unknowns, so we should use both momentum equations. First, set things to 0. The initial velocities of objects 2 and 3 in both x and y directions, and the initial velocity of object 1 in the y direction. Then use geometry, sines and cosines, for the x and y components of the velocity vectors. Now we're going to put all of our knowns on the right-hand side and all of our unknowns, anything attached to M2 and M3, on the left-hand side. I have copied our reduced equations from the previous slide onto this one. Now that we have our unknowns on the left and knowns on the right, we can solve the problem by hand by rearranging one equation and plugging it into the other. Or we can use some advanced math, linear algebra. First, convert the equations into a matrix form. The 2 by 2 matrix on the left, matrix A, has the coefficients of our unknowns M2 and M3 from the left side of our equation. The 2 by 1 matrix on the right, matrix B, has the knowns from the right side of our equation. At this point, you can plug in the numbers into a fancy graphing calculator or use Python. We are solving the matrix equation AX equals B for x, which is a 2 by 1 matrix of our unknowns M2 and M3. In Python, use the NumPy module and linalg.solve function. If you don't remember this, please review the NumPy tutorial from the website numpy.org. This slide shows a Python script to solve the system of equations using NumPy. You need to set up your equations in matrix form as shown on the previous slide, then input the appropriate values for variables shown on lines 4 through 11. Sample output is shown for the dummy data. You are not required to use Python or a graphing calculator to solve a system of equations in this class. You are highly encouraged to practice solving this type of problem by hand. All you need is some algebra, some blank paper, and patience to solve a system of 2 equations and 2 unknowns by hand. However, you may want to use Python or your calculator to check your answers to make sure you have done it correctly. Now let's try a 3-part exercise on kinetic energy and momentum. For a particle of mass m moving with velocity v, the momentum is given by P equals m times v, and the kinetic energy by K equals 1/2 times m times v squared. Part A. Show that the kinetic energy equals the momentum squared divided by 2m. Part B. A 25 Newton backpack and an 8.5 Newton lunchbox have the same momentum. What is the ratio of the kinetic energy of the backpack to the kinetic energy of the lunchbox? Which one has the greater kinetic energy? And Part C. Assume that the backpack and lunchbox have the same kinetic energy. What is the ratio of the momentum of the backpack to the momentum of the lunchbox? Which one has the greater momentum? For brevity, you may use K1 and P1 for the kinetic energy and momentum of the backpack, and K2 and P2 for the kinetic energy and momentum of the lunchbox. Now it's your turn. Pause the video and attempt to solve this problem on your own. After you have your answers, restart the video to go over the solution on the next slide. Here is the solution to the exercise. In Part A, we were asked to show that the kinetic energy equals the momentum squared divided by 2m. Momentum is equal to mass times velocity, so we square it and plug that into the numerator. One of the masses cancels, leaving us with 1/2 times mass times velocity squared, the equation for kinetic energy. We can also rearrange the given equation to write it in terms of momentum. We can use it in Part C. In Part B, we are given a 25 Newton backpack and 8.5 Newton lunchbox, both with the same momentum. We are given the weight instead of the mass, so we must remember that weight is equal to mass times gravity. The ratio of kinetic energies can be written with the equation from part A. We can cancel out the 2's, and since momentum is the same for both, they cancel out as well, leaving us with the mass of the lunchbox, m2, divided by the mass of the backpack, m1. The ratio ends up being 0.34. K2 is larger, so the lunchbox has the greater kinetic energy. In part C, we have the same backpack and lunchbox, but this time with the same kinetic energy. Let's use the second equation from part A to calculate the ratio of momentums. The square root of 2 times k cancels out, leaving the square root of the mass of the backpack, m1, divided by the mass of the lunchbox, m2. The ratio ends up being 1.7. P1 is larger, so the backpack has the greater momentum. So, did you get it right? Want to know more about collisions? The first link is a nice set of lecture notes with examples on collisions. The second link is a fun video about elastic collisions where the digits of pi show up unexpectedly. If you have questions on this lecture, please email your instructor or join a Zoom meeting with a member of the teaching team.